Hello, beautiful people. Welcome back. So this is probably the last uh, lecture of the oscillator series. So I just want to go through an alternate configuration of the phase shift oscillator. So this is actually taken out from a problem, homework problem in the textbook. So let's consider this particular problem below. What we have is we actually have three-stage amplifier, and each op amp was connected to a RC. Okay, each op amp is connected to an RC network, right? So one RC network here, one RC network here, one RC network here. We have three op amp, one, two, and three. And this one is actually virtually grounded. Okay. The first question that we're gonna have is if we're assuming all of this resistance are 1 or 2 or 3, and all of this are a 1 or a 2 or a 3, all of this resistance are the same, and it's gonna be equal to R. And let's assume all of the capacitance are the same one. So um, we need to calculate we need to derive an expression for the frequency of oscillation. So the question in the textbook asks you to prove that the frequency of oscillation is square root of phi over RC. Question number 2 is to, if we assume that all of these amplifier, each of them have equal amplitude of gain, okay, in each amplifier stage. So that means the ratio between uh, RF and RA is equal. Okay. Um, what is the minimum uh, magnitude of gain that's required for each state to sustain its oscillation? Okay. Or in another word is you can actually find what's the relationship between RF and RA, so that you can calculate the gain in each state. Then you can figure out that for your condition of sustaining the oscillation. Okay, so first of all, let's answer question number 1. We need to find the frequency of oscillation. So before we do that, since we're gonna assume all these amplifier stage are the same in the next question anyway, so I'm just gonna go and define RF1 equal to RF2 and equal to RF3, and it's gonna be equal to RF. So from the first amplifier stage, we can see the gain of this stage, including the RC network, to be first, the RC network is going to give me this term of 1 over 1 plus SRC. Second, the op amp amplifier is going to give me um, uh, an amplification of 1 plus RF over R, right? So then since the the first stage take the input VO, right? This VO feed right back in here. It's fed right back in here, and the output of the first stage is VO1. Okay, so I have this term to be the ratio of VO1 and over VO. So now for the second stage, it's taking the input of VO1 and the output of VO2. And if you take a look, second stage is actually absolutely identical to the first stage, so I can just rewrite the same thing. Now for I have VO, okay, VO1 over VO. Now I have VO2 over VO1. Now I need to find the relationship between VO3 over VO2. So I can actually use KCL at this node to find that relationship. So KCL, basically I can break down this 3 current, and if I sum up this 3 current, I will have 0, right? So 3 current, IC3 is this, IR3 is this, and IRA3 is this. So the first term, this current RAC3 is going to be equal to the voltage over the impedance. So voltage is VO3 over 1 over SC3, which is the impedance. Second is this current, IR3, and IR3 will have a voltage of VO3 minus VO2, okay, because it's going in this direction. Then divide for the term R3, and finally we have the last current of RA3. And before you do anything, you have to remember that this node right here is virtually ground. The reason why is because the voltage at this point is equal to the voltage at this point. However, you already have this point to be is grounded, so the voltage here is approximately 0. So you can basically you can assume that to be virtually grounded, ground. Therefore, you have the voltage difference between this and this to be exactly VO3, and if you divide it for RA3, you're gonna have this current. Okay, so you replace that with all of the common thing, like C3 is going to be equal to C, R3 is going to be equal to R, and of course RA3 is also equal to R. You're gonna have this. So you can simplify your expression in terms of VO3 over VO2. You can have this term. Finally, you need to, so you found the relationship between here and here, right? Finally, you just have to find the relationship between this VO and this VO3, and basically you just have to consider this operational amplifier in here, which u again of RF3 over R, because this one is in the inverting configuration, since the input coming to the negative terminal. Okay, so now I have VO3 over VO over VO3. I have VO3 over VO2, VO2 over VO1, and VO1 over VO. I can combine them all together to basically see what's the difference between VO and VO. Okay, so I can write this expression, right? I can basically write this expression, substituting all of the gain terms that I found in here. Okay, and I know that VO over VO is gonna be 1. Okay, I'm gonna substitute of S for J omega. Okay, since I have this one to be square, this one repeat, so this one is gonna be square. This term and this term repeat, so this term also gonna be square. Okay, so what I'm gonna do next is I'm gonna move on of the frequency independent term on one side and the frequency dependent term on the other side. So I have this group is frequency independent and this group to be frequency dependent. Now in order for the circuit to oscillate, of course this need to be like this whole term need to be a real number, right? That means what I can do is I can actually just find a way to get rid of this J component to make it real, so I can assign this whole term to be 0. So now I find the frequency at which that makes this term to be 0. So I set this whole thing to be 0 here with omega naught. I divided both sides by J omega RC, so I have this equation, and finally I can find my omega naught to be square root of 5 over RC, and this is the frequency of oscillation. Next, question 2, I need to find the condition to sustain oscillation. So I'll start with the same equation there, but now I know that if I substitute the omega naught inside, I can actually make this term on the way go to 0. Okay, and I substitute omega naught in here, I can have this, right? I also know what omega naught is because I found that in previous question is square root of 5 over RC. So if I substitute this in here and there's a square, it's gonna become 5 over r square c square. So I substitute that in. Now I can see that r square c square can cancel with this r square c square here. So I cancel those out. Now I have a fraction in here. This is 1 over 2 minus 4 times 5 equal 20. So this one will become negative 1 over 18. So negative side over here, negative side over here is going to cancel out. So I have 1 over 18 fraction in here. Now everything is left with the term RF. So I can solve for RF over R. And it's going to be RF over R equal to 2. So if you want to find the gain of each amplifier stage, you just have to plug in this term. Okay, that's it for this lecture. I put an example, another example in the module, so please review it because I might just want to use it for exam later. The plan for next is I just figure out that in the note I also have active filter. I have active filter I haven't covered, so I'll try my best to finish covering active filter. What might happen is I may just release the exam next week. Then I'll make the active filter question to be extra credit for everyone. Okay, I hope you guys learned something new today, and I'll see you guys next time. Bye.